Well, good afternoon and welcome to KOGA's fifth installment of our summer webinar series brought to you by CountryMark and Ergon. We also like to thank our sponsors as well that have given us their full support of this webinar series, and we do this every week. We'd like to thank the following: AquaClear, Bingham, Greenbaum and Dahl, Bitco, Black Ridge Resource Partners, Britannia, CountryMark, Cumberland Valley Resources, Diversified Gas and Oil, InLink Midstream, Ergon again, Hughes Land, Phil Brown Insurance, Reliance Well Services, Steptoe and Johnson, and Wyatt Terran Combs. Today we're going to feature Dr. William Haneberg, and he is the 13th State Geologist of Kentucky, also the Director of the Kentucky Geological Survey. And more of his biography can be reviewed and read in the chat feature that should appear upon your screen a little bit later on in the presentation. Next week, we will feature Sean Rayford of CountryMark, who will discuss the market drivers for the U.S. oil and industry. So be sure to tune in for that next week. And I was remarking to somebody earlier that this is kind of an unfortunate event that we have such a dynamic rock star lineup of speakers this year, one of the kind of the best assembled group of individuals and speakers, but we can't meet in person. But we have the next best thing. So I'd like to turn it over to Dr. Bill Haneberg of the Kentucky Geological Survey, who will talk about the landslide hazards and pipeline risk. And before I turn it over to him, I just want to make one note. As always, be sure to ask any questions in our Q&A section or the chat feature, and we'll make sure we'll get those addressed after his presentation. So, Dr. Haneberg, thank you for joining us today, and I'll turn it over to you.
Well, thank you, Ryan. I'm glad to be here. Sorry you couldn't be in person. I'm in an undisclosed location somewhere in Kentucky, broadcasting over the internet, and we'll see what we can do with that. I'm also happy to be talking about landslide hazards and pipeline risks because for virtually all of my career as a geologist, dating back to the late 1980s, I focused largely on geological hazards, including pipelines, and have quite a bit to say about it. So there we go. So a lot of you may already know about KGS. Maybe some of you have been working with KGS for many years, but I always like to remind people who we are and what we do in Kentucky in case you're new. But our roots go all the way back to 1838, which is, I think, something to be really proud of, when a group of conservative, influential citizens went to the Kentucky legislature and asked them to support a state-funded assessment of the state's mineral resources. And a geological survey existed in Kentucky in one form or another, intermittently over the next 110 years or so, and the KGS was made part of the University of Kentucky in 1948, and we've been there ever since. And we have a legislative mandate to perform a continuing geological study of the state of Kentucky. We also have a governor-appointed advisory board that was formed in the middle 1980s. So we have 12 people from Kentucky who give us advice. We meet with them twice a year. But I think the most important thing is we don't regulate or advocate or compete. So if you see us there, we're not there to regulate. We don't make regulations, report regulations, or promulgate regulations. We don't advocate for any particular policy outcomes, and we don't compete with commercially available services. So that's important because a lot of things I'm going to talk about today involve information we can provide, make publicly available, but we certainly don't see ourselves as competing with consultants who can also do much more detailed site-specific kinds of work. Also, there's a lot of information out there. So if you're interested in landslides or any sorts of geohazards in pipelines, I think all you have to do is start Googling and you'll be deluged with papers of various kinds, reports by the U.S. Geological Survey, by industry groups like the Pipeline Research Council and the Interstate Natural Gas Association. There's an ISO standard you can see I put there on the screen. There's an ABS standard for subsea pipeline route determination, which doesn't really apply to Kentucky, but I put that up there because I was the manager of the project and actually developed that industry standard. So a lot of information out there. If any of this piques your curiosity, by all means follow up, send me an email or call, and we can get you some more information. Well, in everyday life, when we talk about things like hazards and risks and dangers, we often use them very interchangeably. We stop to think, what do they mean, and are they different? But if you're actually talking about hazard assessment and risk assessment, it is important to make that distinction because they're two separate things. They're both important things, and they're interrelated, but they are two distinct things. So this is a really good graphic I found on the internet distinguishing between a hazard and a risk. So a hazard is something that has the potential to harm you. So in this case, it's a shark. But the risk is the likelihood of the hazard causing harm, or the likelihood of it causing a specific amount of harm, like eating you. So you can say sharks are a hazard, even here in Kentucky, but they're not much of a risk. I think there's very little risk of people being attacked and consumed by a shark in Kentucky, although they're still hazards. Different people define hazards a little bit differently. If you start looking at the hazard and risk assessment literature, you'll see a lot of definitions that are all sort of similar, but sometimes different authors will use different words or different terminology. So in the far right-hand side of the screen there, you can see some different ways that people have expressed risk. As sort of, it can be the product of the hazard and the exposure, basically what could happen and how exposed are you to it. In other cases, it might define it as a hazard times a vulnerability times an exposure, or the severity of some event or occurrence times the probability of that event occurring times the exposure, or the threat times the vulnerability times the consequence, or just likelihood of consequence. So they're all a little bit different, but you can see they all share a similar characteristic, that it basically involves the likelihood that something will happen and then what the consequence of that will be, or in other words, what stands to be lost if that event occurs or is realized. So we'll try to keep that distinction pretty clear throughout the rest of the presentation. Maybe some of you have seen a chart like this. It comes into play in a lot of corporate risk assessment projects. There's a lot on the screen, but we go over it piece by piece. So the upper part, it says consequences. So if you're doing a risk assessment for a project, you can start asking yourself, well, what different kinds of risks are there? Well, there are risks to health and safety. People might be hurt, people might be hospitalized, people might actually be killed. There are environmental consequences, and they might range from something that's slight that can be easily repaired to something that's regional and catastrophic. There are financial risks. And again, those might range from very slight risks to massive risks. Some of you may think back about 10 years or so to the Macondo well incident in BP, and that had an almost catastrophic impact on BP, a global company. But it was a huge impact to them. And then finally, reputational risks. So even if nobody gets hurt and you don't lose a lot of money, there's always a chance that your company or organization reputation could suffer greatly. And we can look at those and say for each of those potential categories of consequences, they can range from none, or slight, or negligible, all the way up to very severe things like multiple fatalities or regional environmental damage or massive financial consequences or an international impact on your corporate reputation. So that's the upper part of the chart. The lower part concerns itself with the probability of an event happening. And depending which version of the chart you're using, this is one I've modified from a publication that came out just the other year about offshore pipeline routing. You might see the probability expressed different ways. In boldface, you see they're very likely, unlikely, possible, unlikely, and very unlikely. Sometimes it's couched in terms of industry experience. So very likely might be something that you wouldn't be surprised if it happened several times per year on a given project, or likely might be several times per year in a company, with the idea that a company has many different projects going on at once. Or maybe it's known once in the history of the company, in which case you'd say, well, maybe it's possible. And then you get to more unlikely occurrences, like it's been known in the industry, but it's never happened in your company, to it's never been heard of in the industry, and that would be very unlikely. And people sometimes try to assign numerical probabilities to that, an annual probability of occurrence. Risk assessing and accounting people really like those values. As a geologist, I'm always kind of skeptical of it. If you're trying to decide if something has a recurrence interval of 10 to the negative 6 per year, that's really, really small, but nonetheless, people try to assign those. So what you would do, and we'll go over an example in a couple of minutes, looking at a pipeline crossing a landslide, and you would go through each of those consequence categories, health and safety and environmental, financial, reputational, ask what the likely consequences would be if something occurred, say if there were pipeline rupture and an explosion, and then you would ask yourself, okay, well, how likely is that over the life of the project? And you would read down from the consequences and across from the probability and rank it as very low or low or moderate or high or very high risk. Some companies or organizations would say, okay, we're never going to do anything that's very high risk. If something is a high or a moderate risk, we'll invoke this concept called ALARC, which some of you may have heard of, as low as reasonably practical, and try to reduce that risk. But we won't take it on unless they absolutely have to. And you might say, for example, that if the company is going to take on a high-risk project, it would have to be a decision at the corporate level, not at the project level, where it's very low and low-level risk to be decided at a project level. One of the difficulties with ALARC is, although it sounds very good, if you get a group of people together in a room, the two bones of contention are going to be the words reasonably and practicable. So people's definitions of what's reasonable and what's practical in order to reduce a risk may differ widely. So it's not a foolproof approach, but nonetheless, it's an idea that's widely used and a concept that's widely known to look at ways to reduce high and moderate risks to levels that are more acceptable, with the understanding that you'll never get to absolutely zero risk no matter what you're doing. So if you want to reduce risk to as low as reasonably practicable or some other level, there's a hierarchy you can go through to try to reduce those risks. And the first one at the top of this inverted triangle here is avoidance. So that's always the best solution. If you don't have to deal with some geohazard like a landslide or an active fault or any other kinds of things you might run into like a sinkhole, your best option is always to avoid it if you can. That may not always be possible. So option number two is to mitigate it. It turns out geological hazards like landslides can be difficult and fairly expensive to mitigate. So often that isn't a really good solution, although it's probably the second most preferable one. If you can't mitigate it, the next option would be to design for it. Basically, if you think a landslide may occur, you can design a pipeline to withstand the expected movement of a landslide. Or if it turns into something like a mudflow or debris flow, you can design a pipeline to absorb that impact. So that would be your third choice. And then finally, the red triangle at the very bottom is fix it, and fix it, and fix it, and fix it, which is the least preferable of all those choices, because you're not really dealing with the problem. You're sort of accepting that you're going to have this continuing stream of risk and things are going to be happening, and it's going to continually cost you time and effort and money to keep fixing it. So in terms of effectiveness, the best thing to do is to avoid it. If you can't avoid it, you mitigate it. If you can't mitigate, you design for it. And if you can't design for it, you sort of have to resign yourself to repeatedly fixing it and hoping nothing really bad happens. And then on the left side, you can see the two-way arrow with monitoring explanation points. So no matter what you do, you always have some responsibility to monitor the hazard and understand if anything is happening. We actually have a pretty timely example. It's something that happened just a couple of months ago in early May. There was a pipeline explosion in Fleming County, a little bit north of I-64, about as far east as Moorhead. It was in the news, and Dave Harris of our energy section sent me an email and said, well, hey, there was an explosion, and they set a location. And as a geologist, the first thing I wondered is, well, what's there? What's on the ground? So it turns out it's an interesting story. So we'll take a look at that, and it's very timely and really well with the theme of this presentation. So the image on the left is an image of the fire from one of the local television stations. The right is a Google map image, and it's showing where that red pin is, the site of the rupture, and you can see the pipeline right away going from the lower left up, sort of snaking its way to the upper right of the screen. So Dave gave me some coordinates, and the first thing I asked myself was, well, what's the geology there? What's the topography there? And what's the landscape like? So I immediately went online and looked it up, and we're really fortunate here in Kentucky because we have statewide airborne LiDAR. If any of you haven't worked with airborne LiDAR, it's a form of laser scanning that lets us do things like mathematically or computationally remove trees. So we have effectively a laser scan of Kentucky with all the trees and vegetation removed. That's incredibly useful if you're a geologist. We also have coming out a series of really high resolution 6-inch color orthophotographs. So the images here are all from publicly available Kentucky from above data. The one on the far left and it's 2 tiles, so it's two 5,000 foot by 5,000 foot tiles. So the total image is 5,000 feet wide and 10,000 feet high. But the image on the left is the color orthophoto, and that's made somewhat transparent and draped over a hillshade map made from the LiDAR digital elevation model to sort of accentuate the topography. And you can see pretty easily where the pipeline right-of-way runs through the image, and then the red circle indicates the area where the rupture was. The second image from the left is a combination of a hillshade and a slope shade map, so it's just a mathematical technique we can use to take these digital elevation data, which are really just a grid of numbers, and we can simulate what it would look like if you removed all the trees and the sun was shining on it from a certain direction and angle up in the sky. So it lets us basically better find subtle indications of things like landslides and faults and sinkholes, and then we use this kind of data quite a bit at KGS. The third image from the left shows the previous image draped with the geology. One of the interesting things you see there is right in the middle of the circle is the Ohio Shale. So shale is a fairly weak rock. The Ohio Shale isn't. The biggest known landslide culprit in Kentucky, those would be the Ordovician Shales, the Cope Formation near Cincinnati, but it is a fairly weak formation, one that can be prone to landsliding. And then on the far right, you can see some of the kinds of techniques we use as geologists to interpret the landscape, and that shows a quantitative estimation of topographic roughness. So basically the orange and red and yellow colors are areas that are rough. They might have shown more recent erosion. They may be sites of landsliding. They can be very useful. So these are the kinds of information we would pull out to understand what the geological setting of a pipeline is, and in particular the circumstances that might be surrounding a pipeline failure. So here we're zooming in to it. The red circle from the previous images is now that heavy red ellipse in the middle. And if you look at that, I'm not sure how many of you are geologists out there, but in terms of the landform, it's almost about as good an example of a landslide as you would want to see. It's the kind of thing you would show a student or an intern and say, hey, this is what a landslide is going to look like when you're looking at airborne LiDAR. It's the hillshade map overlaid with some topographic contours. But I also spent some time looking around for other suspicious areas on the same hillsides in the same Ohio Shale, and those are the lighter colored ellipses. So it's basically, it's a landslide-prone area, and you can see on the right, the topographic roughness map, the pipeline right-of-way it's going through is that smooth sort of diagonal northwest to southwest to northeast path cutting right across the center of the image. So you can see the pipeline right-of-way appears to be going right through a landslide, and looking at some of the details, you can start discerning things like not just one landslide, but some smaller landslides superimposed upon a bigger landslide. You can see a deeply incised stream channel, and as a geologist, we always ask ourselves, well, why is that stream channel cutting down? And one of the reasons could be the land around it is moving up, like it would be in the toe of a landslide. So there are a number of indications there saying that this is basically, it's a landslide-prone hillside, and there's evidence that maybe the movement wasn't actually occurring when the LiDAR was flown in 2017, but there's some good evidence that it's moved fairly recently, and you might consider it to be an active to semi-active landslide. Well, after the explosion occurred in early May, the NTSB came in, and it turns out they issued a preliminary statement just a couple weeks ago on June 22nd, and they wrote that on October 9th, 2018, the area around the rupture was identified by Enbridge, by the pipeline owner, as one of those areas of increased geohazard risk, and that Enbridge planned to remediate the pipelines at that location sometime in 2020 by alleviating strain where necessary and installing strain gauges to further monitor the force on the pipeline. So that's pretty consistent with what I had concluded on the information that Dave gave me going across a landslide, and obviously Enbridge or Enbridge's consultant had realized that as well, and they put it on their list of something to do in 2020. Okay, well, where would that fit into the kind of risk matrix that we looked at before? And I think this is a pretty good example. You can say, well, okay, in terms of health and safety, the pipeline, that particular landslide, the pipeline crossing was pretty much in the middle of nowhere. So we could say maybe the risk to health and safety is negligible or minor, because it's extremely unlikely anybody would be near that particular point. If this was going through an inhabited area, through a town, next to a subdivision, we might rate that much higher, but because it was in the middle of nowhere, we could say that probably the health and safety risk is low. The environmental risk might be pretty minor, because it's a natural gas pipeline. You wouldn't be spilling a lot of oil. You'd have some methane emissions, maybe you'd have smoke, you'd have CO2. Financial, that might be major. It was a 30-inch interstate transmission line, so the cost of repairing that, in addition to lost revenues, I said, well, that might be major. And reputational, well, it was on the local news in central Kentucky. I don't know that it was ever on the national news, and it certainly wasn't on the international news. So the impact there was probably local. So we can take the highest of those, the financial consequence, and move down. Then we can say, well, how likely is this, was this to have happened? And I picked possible here because we could look at the airborne LiDAR. We knew it was a landslide. There were some signs that movement of the landslide could have been recent or ongoing. So we'd have to say it's probably possible. And you look at where those two intersect and you come out with a high risk. And again, I think that's pretty consistent with what was in the NTSB report. If it was scheduled to be repaired in 2020, this isn't something where they said we're going to have to deal with this in 10 years or 15 years, but rather something that needs to be dealt with in the next year or two. So that's an example of a way you can use this matrix to look at a particular landslide crossing along the pipeline route. Okay, so what are we doing at the KGS that might be able to make the situation a little bit better in Kentucky? And it turns out we have a group of people who work on landslides. Matt Crawford, we'll talk a little bit about some of his work later. He's the principal investigator for a big FEMA-funded project we're doing in the Big Sandy District. With Jason Dortch, who's a really outstanding geomorphologist with a lot of experience looking at landscape evolution landslides. Hudson Koch, who joined us to work on the FEMA project. Dr. Yishan Zhu is a postdoctoral researcher at KGS. He came to us from Texas A&M for a couple of years. Sebastian Bryson is a professor in civil engineering at UK. I'm active in the group. And also Sarah Johnson, who is a geology instructor at Northern Kentucky University, and also working on her PhD at UK looking at landslides. And in addition to the people, we have some facilities. So one of the things we did a couple of years ago was make an investment to set up the KGS Digital Earth Analysis Library, or we call it DEAL, which has some high-end workstations and file servers, and we have the entire Kentucky LiDAR data set stored there locally, so we can actually work on developing applications of this tremendous airborne LiDAR asset we have in Kentucky to help solve geological problems within the state. So in terms of specific things we have available in Kentucky that might be useful for understanding landslide hazards and especially how they're related to pipeline risk, we have the KGS landslide database, and you can get these, by the way, all online. These are the screenshots from our Kentucky Geological Map Service, and there are all kinds of layers you can turn on and off. So this shows our landslide database, and if you click on any of those, depending on the information we have, it'll tell you where it is, when it occurred, if it was associated maybe with heavy rainfall. It varies from landslide to landslide, but it's basically everything we know about landslides that have occurred in Kentucky. Some of the drawbacks of it are that if you were to zoom in, you'd see that the landslides are concentrated, especially along roads, because that's where people see them most often. If there's a landslide along the road, somebody's going to see it, somebody's going to report it, maybe the road will even be closed. The landslide occurs up in the hills someplace, maybe nobody will ever see it, nobody will ever care. So it's an incomplete representation, but it does give you some idea about where the landslide problems are, especially in eastern Kentucky and southeastern Kentucky, and also for different geological regions in the Cincinnati area. The Cincinnati area is one of the most landslide-prone cities in the country. And then we even have landslides scattered all the way out to the Mississippi River bluffs in far western Kentucky. So this is sort of our first layer of landslide information is the database map that we can access through our website. And the landslide database map includes a number of different things. One is a layer of landslide showing on geological quadrant limits. So For those of you who don't know, we're also very fortunate here in Kentucky to be the first state to have completely mapped the geology of the state at a detailed scale of 1 to 24,000. And on a lot of those maps, if there were landslides that were big enough and obvious, the landslides are actually shown. So this layer shows the landslide shown on geological quadrangle maps. It's a pretty sparse representation because in order to get on a geological quadrangle map, a landslide has to be pretty big and obvious, but nonetheless, we're able to separate those out. Another class of information we have are landslides mapped from area photographs, and those were primarily done by the U.S. Geological Survey in the 1970s and the 1980s. And you can see by the sharp boundaries on those that a lot of those were done as part of a project focusing on southeastern Kentucky. So again, it doesn't cover all of the state, but they're pretty good maps for the age of them. They're pre-LiDAR maps made from aerial photographs and maybe with some topographic maps to supplement those. But those are a relatively good layer where they exist, and those are, again, freely available to anybody who would like to use them. Landslides mapped from LiDAR images. So LiDAR is a much more recent acquisition in Kentucky. We finally achieved statewide coverage just a little over a year ago, but nonetheless, we've been working on it. You can see a couple of areas up near Cincinnati where Matt Crawford has done a lot of mapping. Sarah Johnson has also done some work there with people from Northern Kentucky University. And then there are two areas in eastern Kentucky. The square area is the Prestonsburg Quadrangle, and the more regular areas of Coffin County. And over the past couple of years, we've had two separate student interns, one from Kent State University and one from Morehead State University, and they have mapped landslides in those areas as part of their internship project. So we have that available as well. And then we'll be talking about one more big step that we're still working on right now. One of the really neat things is that the Kentucky Landslide Database gets fed into NASA's Global Landslide Database. So I've turned on all of the United States, or at least the conterminous United States here, and parts of Mexico and Canada. You can see all the orange dots are the things that the U.S. Geological Survey Global Landslide Database listed. Some are in Kentucky. The red dots are the information we added from Kentucky. And there aren't a lot of states that have this level of landslide inventory. So again, we're in a really great position that we have far more landslide information than a lot of states do. Oregon and Washington and California, of course, have a lot, but for an eastern state, we have quite a bit of landslide information that's publicly available, and it's incorporated into the NASA map. The NASA map is also neat because you can see the background coloration shows overall landslide susceptibility. You can get things like real-time rainfall. You can get a near real-time landslide forecast for different parts of the world. So I think it's really neat that we can actually be involved in that and contribute Kentucky data to a much larger global landslide picture. So what are we working on at KGS in terms of landslides, and especially in terms of things that might be useful for assessing the risks to oil and gas pipelines in Kentucky, whether they're small diameter gathering lines or large diameter interstate transmission lines. The biggest project we're working on now is a FEMA-funded project in the Big Sandy area development districts. That's Floyd, Johnson, Magoffin, Martin, Pike counties in eastern Kentucky. That's combining LiDAR-based landslide mapping, so we're using statewide airborne LiDAR coverage to map landslides in those 5 counties. And we're also doing some physics-based and statistical hazard modeling. So the physics-based model combines the basic physics of landslide initiation with some probability theory to take into account the fact that we don't precisely know all of the information, and these high-resolution digital elevation models to actually do a calculation about the slope stability. The statistical hazard modeling, we actually use the mapped landslide locations, and then we look at everything we can find, the steepness of the slope, the curvature of the slope, the roughness of the topography, and we put those all into a big equation and come out with a landslide hazard based upon those sort of geometric variables. And then finally, we're doing a risk estimation, and then I'll show you an example of that in another slide or two down the line. We're also interested in multi-temporal change detection using repeat coverages of airborne LiDAR, but also drone-based LiDAR and drone-based structure for motion photogrammetry. So the question is, if you have one LiDAR flight and you wait a year, 2 years, 5 years, and do another LiDAR flight, what can you see? And the image on the lower right there, you see a little blue and red area with the arrow pointing to it. That's a landslide along the Ohio River Valley in northern Kentucky. that was detected by looking at LiDAR coverage from 2012 and 2007 and just subtracting to find the difference. So that's an area of active research. We're also looking at climate change and regional landslide hazards, how changing precipitation patterns are going to affect landslide hazards in the Commonwealth, earthquake-triggered landslides, especially in western Kentucky, land use and long-term landscape evolution over hundreds of years. And then finally, back in 2018, we also contributed a statewide landslide susceptibility map to the state hazard mitigation plan. So we're actually working on a number of different things. Here's some of the LiDAR for the Big Sandy area. The image on the left is just an uninterpreted hillshade map, giving you some idea how rough and complicated the topography is. And then a human being goes through and actually maps out landslides, as you see on the right, and assigns to them some degree of confidence based on how certain we are that it's actually a landslide. And that's some of the information we use as the basis for landslide susceptibility work. And then here are two of the model results. The one on the left is the physics-based probabilistic model, where it tells you the probability that, given the information you've supplied to the computer program, that there should have been or will be a landslide there. So that ranges from 0 to 1 or 100% probability. And on the right is the statistical model, where basically it doesn't include any physics at all. It basically just looks at the properties of the landscape where we know there are landslides and then tries to extend that to other areas. And the good thing is, although there are some differences between these two, they're pretty close. You can see a lot of similarities between them. So that gives some confidence that we're on the right track. You approach a problem from two different directions and you get pretty much the same answer. But still the question is, well, how can this be used to better plan pipeline routes or manage pipeline routes or assess pipeline risks? And this is where we're really starting to get some neat answers. Is we're actually using those previous layers as input for risk analyses. And then this is just a preliminary ongoing map. It's sort of our working version. It's not a final version, but we're actually calculating the risk in terms of the hazard, those map landslides we just showed you, and the exposure. Basically, if what's there, is there a road there, is there a building there, is a house there, is there a hospital there? If it's a building, maybe it's an empty warehouse and it's not as much risk as if it's a hospital or a school or a fire station. And then the vulnerability, what would it cost, what would be the economic damages if that facility were damaged or destroyed by a landslide? And you can see it would be just one more step to overlay a network of, say, gathering lines or interstate transmission lines over this and incorporate another element of exposure and vulnerability in and do risk assessments along pipeline routes using this kind of approach. The big caveat is we're still working on this. The project runs into next year, so we're still refining the best ways to establish the costs of damages and the exposure. We're using building footprint maps that are widely available, things like highway maps, railroad maps. But we could conceivably pretty easily incorporate a pipeline network map into something like this and actually map risks along different segments of pipelines. And then finally, looking at what you can really do. This is work that I actually did in Houston before I came to Kentucky, but a lot of the work we did there was doing risk and hazard assessments along export pipeline routes in very deep water. We would often be working in water up to 10,000 feet deep and trying to figure out the best routes for pipelines through very hazardous seafloor conditions. And we developed a technique where you make a map essentially showing the risk. We call it geocost, but we would map high-risk areas and low-risk areas and medium-risk areas. And then within GIS, you can give it a starting point and an ending point and basically tell it to find you the route that has the lowest overall risk. And that's what you see up in the upper left-hand corner where it says best estimate, and you can see the pipeline route is sort of snaking its way to avoid the orange and the red areas and follow the blue and green areas as much as it can. But the one thing we know is that there's a lot of uncertainty related to that. You're working in an area that might be literally 2 miles underwater. It's dark. No human can ever go there. You have to do everything remotely. There are limits to the resolution of the data. So there are a lot of uncertainties. So what we can do is go into that best estimate and use some pretty complicated computational techniques and take random samples of that map and then generate different versions of the risk map that are statistically equally probable or equally likely to occur given that uncertainty, and then run the pipeline route over and over and over again. In the real case, you might do this, say, 100 different times and come up with a corridor that represents the least risk. And then that's where, in subsequent steps, we focus our efforts on to better characterize that and better understand the hazards and decide where that hazard hierarchy we talked about earlier of avoidance and mitigation and design, what actions we can take to further minimize the risk. So I don't know that anybody is doing this in Kentucky at this point, but certainly given the kinds of information we're producing and the ways we've been developing to assess landslide risks in Kentucky, and particularly with the geology and the geological conditions that we have that are unique to Kentucky, it's certainly something that could be useful for selecting new routes for any kind of linear infrastructure in Kentucky that would include oil and gas pipelines. And with that, I'll wrap up and just remind you, if you want some more information, write or call or visit us on the web, and we'd be happy to talk to you and provide whatever information we can. So thank you.
Well, thank you, Dr. Haneberg. I do have a few questions if you have some time.
Sure.
First of all, how does Kentucky rank in comparison with the rest of the nation on the occurrences of landslides?
Well, if you, or actually I can, let me, there you go. So this provides a good overview. It's an NASA map again, but if you look at the colors in the background, that gives you landslide susceptibility. So you can see the Appalachians are actually kind of a hotspot for landslides until you get to the Oregon and California coasts. There's some areas in Idaho and Montana here and throughout the Rocky Mountains. So it's actually, even though you might not think of Kentucky as landslide territory, it is actually kind of a hotspot compared to a lot of other areas because we have steep topography, we have a lot of fairly weak rocks, we're a fairly wet and humid area. So it's, Eastern Kentucky especially would be fairly high on the list in terms of regional landslide hazard. So it's certainly much higher than Kansas or Oklahoma or a lot of parts of Texas. Probably not quite as high as maybe Western Washington or Western Oregon, where they can easily get 100 inches of rain a year, plus have things like earthquake hazards. But we're still fairly high on the list. A lot of people don't realize this, but in an average year, landslides cause more economic damage in Kentucky than flooding does. So that might give you some perspective on the issue.
Thank you for that. Another question is, whenever there is a landslide or let's say a sinkhole that developed, does the KGS have a response team that goes in and studies that? Are they asked to? Or how do you guys, analyze that post-incident?
Yeah, a lot of that depends on the context. So we're always willing to talk to people if there's a landslide or a sinkhole or something happens. We're always willing to provide direction to whatever information we have. Especially because we don't compete with private consultants, if it's something that's on your private property, it may not be a public matter for us to look into. If there is, though, say, a public safety issue, if there's a landslide along a road, we may be contacted by, say, a county emergency manager and asked to look into it. So I think the context would depend. If you just have a sinkhole on your farm and you call us, and we'll probably tell you all the information we can and then recommend that you contact a licensed engineering consultant to look into options for remediating it. And the same thing is you have maybe a small landslide that's blocking your driveway. If it's affecting public safety or something like a state highway, then we may be asked to help by the state by the county emergency manager, maybe by the transportation cabinet. I don't know if anybody remembers last summer, there was a regional New Madrid earthquake exercise, and we actually contributed to that. We had people from KGS during this week-long exercise in the state emergency information center with the idea that if a large earthquake actually occurred, we would be there to provide information to the state level emergency managers on things like aftershocks and locations of landslides and geological conditions that could be contributing to abnormally high levels of damage. So yeah, it all depends on what the context and what the circumstances are.
And I have two of the same question. This is a popular question here. What are the factors that you have taken into account while considering high-risk areas for landslides?
Well, it basically follows that formula we look at in one of the slides. Let me. Yeah, so there you can see the equation. So the hazard, we in the version we're working on now, we get that from the statistical model. So we map the landslides, we know the sort of the habitat of landslides, and we apply that over the entire 5-county area. So that gives us the hazard. The exposure is whether or not something's there. So if there's nothing there, then a landslide could damage, the exposure is essentially zero. If it's right next to say a U.S. highway as compared to a state highway or a county road, that would be an increasing degree of hazard. It might be, exposure. So the exposure might be very low if it's a county road versus a large U.S. highway. And then the last thing would be the vulnerability. What would it cost to repair or replace this? And that gets a little bit more complicated. That's one of the things we're working on now, is asking, well, okay, we may be able to estimate how much it costs to fix the road or rebuild the building, but what happens if that road cuts off commercial traffic and people now have to drive an hour out of their way to get to work? Or if somebody is in business and you're transporting something, if all of a sudden your trip length increases, so it's going to take you more time and more money. So the basic information we use is what's the landslide hazard, what's the exposure, what's there that could be damaged by the landslide, and this is a layer where we could add something like pipeline routes, and then the vulnerability. What would the cost be if a landslide were to damage or destroy that? Right now, we're also dealing in terms of low, moderate, and high, because the cost estimates we get have a lot of uncertainty involved in it. So we don't want to say it's $1,000 per square foot or something like that. So we're still trying to figure out a way to normalize all these different cost estimates from different sources. But those are in the current risk mapping, we're doing the 3 pieces of information we use. What's the hazard from landslide? What's the exposure? What's there that the landslide could hurt? And then the vulnerability, what would be the loss or the consequences if the landslide were to occur at a certain point.
Okay, and the last question I received is, are there any upcoming projects that you're working on that may be federally funded, received any grants to study any landslide projects?
Well, the Big Sandy project we're in the middle of, and that's going to end sometime in this coming spring. So that was funded by FEMA. That was originally a 3-year project, but they condensed it down to 2 years. So we're now trying to do 3 years of work within 2 years. So that's a FEMA-funded project. Matt Crawford, who I mentioned earlier, is involved with a NASA space grant project with Sebastian Bryson in civil engineering. A lot of our geological mapping, we receive funding from the U.S. Geological Survey every year to map typically 4 7.5-inch quadrangles. Those aren't specifically focused on landslides, but they are superficial geologic maps. So if there are landslides there, they would be included on the maps. So yeah, just off the top of my head, there are a number of things where we receive federal funding that supports our landslide studies in one way or another. We also just recently started a FEMA-funded sinkhole study. So we're going to do the same sort of thing, but with sinkholes in Kentucky. So yeah, we do receive a fair amount of federal support for this work. And I think also the really important thing too is we use that to leverage state funds. So virtually all the federal funding we get requires a match at one level or another. The USGS projects are typically a 50% match. So Kentucky has to come up with an equal share to the federal government for most U.S. Geological Survey projects. So we couldn't do it alone, and the federal government could do it alone, but working together with them, we can do quite a bit.
Actually, I had 2 more questions slip in.
Sure.
So a very popular discussion today. Are your landslide maps available on the KGS website that could be used by our members for planning purposes for permitting?
A lot of them are. Let's see. Wrong instruction. So yeah, this is available. So this you can get this on your phone right now or your desktop computer. So this is available through the Kentucky Geological Map Service on our website, and within there you can turn on and off layers to see the different categories of landslides. One of the issues here is you can see in the areas where the coverage exists, it's pretty dense, good coverage. But if you go beyond those areas, there's less information, but all this is available. These, I think, are all available because they're on the map service. The things that aren't available, here's the USGS maps, and then that's publicly available. You can download their database. The things that aren't available are this ongoing Big Sandy project, because that is still in progress. Once it's done, of course, it'll be publicly available, and as part of the process, we're meeting with the county emergency managers and the Big Sandy ADD people. So this will eventually be available. The other thing that's available, not through us, but from the Kentucky From Above website, and that's run out of Frankfurt, is all of the statewide LIDAR. So that's another completely free public resource that people can use. So it doesn't actually show where the landslides are, but if it's an area where we haven't mapped the landslides yet, and somebody wants to do that, if you have a geologist on your staff, or if you have an engineering consultant you work with regularly, that they can get the same LIDAR data that we use, and we're happy to talk about the techniques that we use and explain to them how they do it. So the answer is yes. If it's in an area where we've done the work, that's all publicly available, or will be publicly available as soon as the project is done, and the LIDAR coverage is available for the entire state for people to use on their own.
Thank you for that. And the last question that I received was, how have you characterized the landslide? Have you considered the slope, angle, direction, elevation, et cetera? Is there a good resource for that?
Oh, yeah, that's exactly what the LIDAR is. So the LIDAR data set gives you, if you were to imagine sending a surveyor out and having that surveyor every 5 feet measure almost down to the inch the elevation of the surface and get a grid of every 5 feet across the entire state of Kentucky, you would have a very precise measurement of the elevation. That's what the LIDAR data set gives you. So it gives you 46 billion points covering Kentucky. So in all these nice, pretty shaded images I show you, they're actually underlain by 46 billion numbers. So we can calculate in great detail the slope. We can even calculate how much steepness and slope varies from place to place. So yeah, we include all of that. We include whether the topography is bowl-shaped and tends to serve as a catchment for water during heavy storms, or if it's sort of bulging convex shape that would tend to shed water. We can combine that with a geological map to say, well, okay, different soils develop on different kinds of bedrock, have different strengths. So yeah, we use all of those things in excruciating detail using, as we're looking at here, the logistic regression model. That includes something like, originally when they started out, I think 22 different variables. So slope steepness and slope roughness and the curvature of the slope, and whether the slope was north facing or south or east or west facing. We can include vegetation in that. We can include the rock type. And then the complement to that is the PISA-M rational probabilistic model. So that actually looks at the physics of forces acting in the slope and the actual strength of the soil and the steepness of the slope. So yeah, we use all those things in great detail. And we could probably talk for days about all the different ways we combine that information, and then evaluate also what is the most useful information out of all those possible pieces of information. Now, some of it's not going to tell you a lot. So you can go through it, do the analysis, and say, well, okay, these 5 variables are the most important, and the other 20 variables don't really tell us that much. So you keep the 5 that tell you the most, and you don't worry about maybe the 20 variables that don't tell you so much. So yeah, we use all kinds of information like that.
Perfect. And I see that Dave Harris of the KGS has joined us as well. So if there are any, last or, parting words from the Kentucky Geological Survey, speak now, forever hold your peace. But we really appreciate you both jumping on here, and Liz last week hopping on, and I believe we have one more from the KGS in a couple of weeks. So we appreciate all that you do for Kentucky oil and gas industry, not only just the industry, but just everything else. So I'll turn it over to you for any last words.
Yeah, infamous last words. Call it right. If you have any questions, we're always happy to do whatever we can. And all of our information we make publicly available, and it's free. So our sort of motto is we try to make as much information as easily accessible to as many people as we can. So if you want to follow up on any of this, call or write, and we'll be happy to talk to you.
Perfect. Well, thank you so much, Dr. Haneberg. We really appreciate your time and engaging in this very informative discussion with the industry and the Kentucky Oil and Gas Association today. Before we part, I'd like to thank Emily Childers last week, who filled in for me, who did a great job of filling in, as well as Stacy Dover and Michael Nelligan, who run the show every single week. So I really appreciate their dedication and time. I know they have really busy schedules as well. So thank you again. We thank our sponsors, and next week we'll see you here next Tuesday at 2 p.m. Eastern. Thank you again, and we'll see you guys next week.
Thank you.
Thank you.